right, we're moving on in our discussion about how to simplify and solve circuits. I'll introduce two methods and then we'll talk about each individually here. The two methods are called the node voltage method. Sometimes those are reversed, and this is called the voltage node method, and the mesh current method. Now, these two methods simplify the number of equations that you have to solve. For example, if KVL, KCL, you have a whole bunch of equations with a bunch of unknowns. It's kind of messy and probably the hardest way to solve. Well, this reduces down the number of equations that you have to have. And this is another method that does sort of the same thing, but they both just reduce down the number of KVL or KCL equations. And the way that they work is that mesh current method requires that your circuit be a planar circuit. The node voltage method will work if it's planar or non-planar, but for a mesh current it has to be a planar circuit. Now, a planar circuit is just a circuit that can be drawn on a plane. In fact, every circuit that you've seen so far in this class has been a planar circuit. Let me show you some examples here in the textbook of what a planar and non-planar circuit might look like. Look at this one here. This one is a planar circuit. Now, once again, I'll say it this way. A planar circuit is a circuit that can be drawn on a plane without crossing wires or without crossing branches. This is a planar circuit. I know it shows a couple of wires that are crossing here, and you might think, well, that disqualifies it as a planar circuit. It's a non-planar, but you're wrong, because this can be redrawn as a planar circuit. Here, in fact, here it is right here. You see that R7 resistor is taken out and stretched around the outside, so it still makes a connection between the top and bottom where it was connected previously. It's just now drawn so that none of the wires are crossing. So again, a planar circuit, none of the wires are crossing each other. Okay, but here's an example then of a non-planar circuit. For this one right here, you may be able to take some of the wires, like this R8, you may be able to take it outside and run it around, but you can't do that with the R8 and the R10, and also do it with the R7 here the way you did up here. Up here you had plenty of room, but when the R8 goes outside, if you did the same sort of thing you did here with the R8 resistor down here, then that doesn't leave room for the R7. So this is an example of a non-planar circuit. The point here is that mesh current requires that your circuit be planar. Node voltage will work with anything though. Okay, now a couple of other things regarding these methods. Let's say, for example, we have B sub E. Let's say B sub E is the number of essential branches that you have in a circuit. Now, the number of essential branches is also the number of currents, which are typically the things that you're trying to solve for. So those are the unknowns. So B sub E is equal to the number of essential branches. Let's now let N sub E equal the number of essential nodes. All right, well, if that's the case, then B sub E is the number of unknowns. You need B sub E equations in order to solve for your unknowns. Well, from KCL, we were able to derive N sub E minus 1 independent equations using KCL. But for KVL, that's where the rest of the equations came from. Well, how many equations did we need then from KVL? Well, we needed the rest. So we needed B sub E minus N sub E minus 1 equation. If you take those two things right there, you add them together, you end up with B sub E, which is the number of equations you need to solve any circuit that you're trying to solve, because you have B sub E currents and B sub E unknowns. The node voltage method reduces down the number of equations that you need to solve a circuit to just N sub E minus 1 for the whole circuit. And the mesh current method does the same sort of thing. It reduces down the number of equations that you need to this right here, which would be the number of KVL equations. And it allows you to solve the circuit with just that number of equations right there. Node voltage, you only need N sub E minus 1 equations to solve. mesh current method, you need B sub E minus N sub E minus 1 equations to solve the circuit. That reduces down the number of equations significantly. Whereas for KVL and KCL, you had to have both of those. You had to have B sub E equations. So these methods, node voltage and mesh current, are very powerful methods, and you can get to a solution a lot quicker. All right, let's talk about the node voltage method. With this method, you can outline the number of steps that it takes to solve a circuit. Let's do it this way. Step 1, find all of the essential nodes in your circuit. That is going to be N sub E. That's the number of essential nodes that you have in your circuit. You need to be able to identify those easily. Step 2, flag one of those essential nodes as your reference node. Now that's going to be the node that you refer the voltages at the other nodes to. So it'll make more sense later on, but you need to be able to flag one of those essential nodes and call it the reference node. Step 3, you need to define the node voltages for the non-reference nodes. So you flagged one of those essential nodes as your reference node, and then you define voltages for the other nodes, which would be the non-reference nodes. And how many of those are there going to be? There's going to be N sub E minus 1 of those. Step 4, you derive node voltage equations for all of the non-reference nodes. That means you're going to have N sub E minus 1 of these node voltage equations. And finally, step 5, you solve the circuit. Now, solving typically means that you're finding node voltages. Those are the things that you defined back here in step 3, the node voltages. And once you've got the node voltages, then everything falls out from there. And this will make much more sense when we actually get into an example, and let's do that right now. All right, here's our circuit. We've got two sources here, one current source and one voltage source. And then we've got this arrangement of resistors here. All right, well, let's follow the steps and see if we can solve this circuit. And when I say solve the circuit, I mean literally you could find all of the currents, you could find all of the voltages across everything. So all currents and all voltages would be solving the circuit here. All right, step 1, let's find the essential nodes. Well, if you should be practiced at this by now. This is an essential node. That's an essential node. In fact, all of that right there is an essential node. And then all of this across the bottom is also an essential node. So it looks like we've got 1, 2, 3 essential nodes here. So that means what? N sub E is 3. We should be able to write N sub E minus 1 node voltage equations for this circuit then. Okay, second step. Let's flag one essential node as the reference node. Now we've got 3 essential nodes here, so how do we know which one to flag? Well, experience is going to teach you which one is the best option, but let me give you a general rule of thumb here. The general rule of thumb here is flag the one essential node as the reference node that has the most things coming into it. Now here's what I mean by that. If you look at this essential node right here, there are 3 wires connected up to it. So there are 3 things connected there. Here, there are also 3 things connected. But down here, look, there's 1, 2, 3, 4 things connected. So this would be a good option, at least initially until you get some experience. This would be a good option to flag as the reference node. So let's do that. And here's the way you do it. Just anywhere along here, put a flag that indicates that that's the reference node. Now by doing that, what we're doing is we're defining this as our, you could effectively say that's 0 voltage for this node right here. All of the other voltages are going to be referenced to this node. So that's why it's called a reference node. Step 3, define the node voltages for the non-reference nodes. Okay, well, how many non-reference nodes are there? That's these 2 up here. And we define node voltages. Now, that just means assign variables to these other reference nodes. So let's say the voltage at that point, let's call that voltage 1. And the voltage over here, that's voltage 2. And by doing that right there, we have defined our two non-reference node voltages. And that's it. That's as simple as that. So we've done step 3. We're on step 4, derive node voltage equations. Okay, this is the trickiest part. Not hard, but you just need to see it to fully understand it. For each of these nodes here, we're going to define a node voltage equation. Now here's the way it works. Let's start with node 1 here. The one that has the node voltage of V1. That's the one I'm calling node 1. Think of it as a node where all of the currents are leaving that node. Okay, if this was current I sub A, and this is current I sub B, and this is current I sub C, then you could write a node voltage equation that looks, a KCL equation, that's what I should have said. You can write a KCL equation for this node that looks like this. I sub A plus I sub B plus I sub C has to equal 0. That's the sum of the currents leaving is equal to the sum of the currents going in. All right, now with that equation right there then, you change this to be in terms of the voltages, in terms of the voltage V1. And let me show you how to do that. When you write an equation for this node voltage here, or that involves this node voltage here, you write it this way. You start at the V1. That's the first voltage. Then you're traveling through that 1 ohm resistor, and that's a drop. So you would subtract off I sub A times 1 ohm. Then you pass through the 10 volt source, and since we're going down here, it's a drop of 10 volts, so minus 10. And then we're at the bottom reference node, and we can call that 0. So we went from here, passed through that, dropped that, and then this is the equation for that. All right, but what we want is we want to solve it for I sub A. Now, take this equation right here and solve for I sub A. If you do that, you end up with this, V1 minus 10 over that 1 ohm. Now this is 10 volts, and that's equal to I sub A. So that's what I sub A is. In other words, it's V1 minus 10 volts over the resistance, which is just 1 ohm. Now we add to that I sub B. But I sub B, if you do the same sort of thing, V1 minus 5 I sub B is equal to 0, then you would solve it and get I sub B equals V1 over 5 ohms. And now if you do the same thing for I sub C, you do the same sort of thing. Let's write that equation though. You start at V1, you pass through the 2 ohms, so that's minus 2 I sub C, and then you end up over here at V2. So what is I sub C? Well, I sub C is V1 minus V2 over 2 is what I sub C is. So write that here, V1 minus V2 over 2, and that's equal to 0. So all of that summed up is equal to 0. Now we'll be able to write the node voltage equations without going through all of this every time. You'll figure out that real quickly you can write the node voltage equation just by inspection. That one's, you talk about the current that's leaving that node. Well, that's V sub 1 minus 10 over 1. You talk about the current that's going down the center. Well, that's going to be V1 over 5. You talk about the current going to the right. Well, that's just the difference between the two voltages divided by the resistance. So each one of those pieces of this equation here, you should be able to write just by inspection. Now this is the node voltage equation for node 1. So we've just written the node voltage equation. Let's draw a box around it because we're going to need to use that now when it comes time to solve. But we need to write a second one for node 2. Now when we get to the node 2 equation, you forget about these currents over here. Forget about those. Those were just something you had when you were at node 1. Now you got your own currents over here, and let's talk about them as if those currents are also leaving this node. All right, well then what's the current going to the left, and what's the current going down, and what's the current going to the right? Well, let's write down the node voltage equation because all three of those currents should sum up to be 0 as well. All right, by inspection then, the current that is going to the left here is V2 minus V1 over 2. That's the current going to the left. The current going down is V2 over 10. And what about the current going to the right here? There's no resistors in this section, but you know what that current is. That current is 2 amps. Well, it's 2 amps coming into the node. We want to write the current as if it is leaving the node. So that would be plus negative 2, and that's equal to 0. All right, here's our second node voltage equation then. We need to take these two right here, and if you look, there's 2 equations, 2 unknowns. The unknowns are V1 and V2, so we need to solve that. I'm going to rewrite those equations on a separate sheet of paper. There we've got our 2 node voltage equations, and now it's time to solve these. Well, you know how to set up a system of equations. It's got 2 unknowns. You need 2 equations, and that's what we've got. So you should be able to solve this fairly easily, but let me show you a trick. The world is full of tricks. Look at this top equation. Let's call this equation 1. This will be equation 2 here. All right, look at equation 1, and we can rewrite that. Let's find a common denominator, and what would the common denominator be for all of these? Looks like 10. So 10 is the common denominator. Now what do I need to multiply this first term by to get the bottom 10? I need to multiply by 10. So I'm going to have 10 V1 minus 10 times 10 is 100. And now what about this one? Well, I need to multiply by 2. What about this one? I need to multiply by 5. See what I did there? Now all of this should be over 10 and it's equal to 0. But just imagine I put it over 10 and then I multiplied both sides by 10. And when I do that, the right hand side is still 0 and the 10 that's on the bottom of the fraction goes away. So I just write this and I'm done. Okay, now we can add up similar terms here. Looks like I've got 10, 12, 17 V1s. So 17 V1 and minus 5 V2s and minus 100. So we could just say that's equal to 100. Let's do the same thing for equation 2. Look, what's the common denominator? Well, once again, 10. Okay. Now it just happened to be that. It may not always be 10 for both equations, but it is in this case. So I need to multiply this 5 V2 minus 5 V1 plus V2 minus, now multiply by 10, so that's going to be 20. And that's equal to 0. Let's combine our like terms. Looks like we got minus 5 V1 plus 7 V2 is equal to 20. Now here are our 2 equations with our 2 unknowns, and it's written down a little more simply so that you can plug those into your calculator. Hopefully by this point you know how to solve simultaneous equations. We're going to do this over and over again. If you don't know how to do it, get it done now. Well, let's see if we can solve this. I better double check. Looks like I made a mistake right here. That should not be 7, that should be 6. So that's a big O6 right there. All right, now that you've done that, you should be able to solve. And because it's only two unknowns, you could theoretically do this by hand, but don't waste your time. Learn to use your calculator instead. If you solve for V1, you get 9.09 volts, and V2 is 10.91 volts. Okay, now that you have V1 and V2, what does that give you? Well, let's say you wanted this current over here. You want this, what I've labeled as I sub A. You want that current. Well, what is that current? Well, it's just this right here. That current is V1 minus 10 over 1. So V1 was 9.09 minus 10 over 1. There, you've got the current. And now that you've got the current, could you figure out what the voltage is across this? Yes, you could. Okay, so you could write V equals IR for this one resistor to figure out what the voltage is across it. And the same sort of thing here, the currents, this current between these two, if I want it to go to the right, that current is going to be V1 minus V2 over 2. But if I want to define it as going to the left, then that current is V2 minus V1 over 2. You'll get the same value for both of those currents, but one will be positive and one will be negative. And once you've got the current, you can figure out what the voltage drop is across that 2 ohm. And conversely, you can figure out what the power is across any of these elements. What's the power across the 2 amp here? Well, it's just P equals I times V. So if I wanted to know the power of the 2 amp, P equals I. Looks like I is 2 amps here, if I want it to be in that direction, times V, and V is V2. The voltage across the 2 amp is V2. So multiply those two together and you've got the power then. So you see, once you've got V1 and V2, everything else just falls into place. You can calculate currents, you can calculate voltages, you can calculate powers. So the secret then is to find V1 and V2. Okay, let's do another problem then so that you can practice this. All right, there we go. There's our circuit. Once again, we've got two sources and some arrangement of resistors here. And let's say for this specific problem, we want to know what is this voltage from that node down to the bottom here. What is that voltage across that? Okay, let's follow the steps again. Step 1, let's define our nodes. Looks like we've got a node over here, a node over here, and a node across the bottom. Now, those are essential nodes, not just nodes. So we've defined our essential nodes. Okay, let's flag 1 as the reference node. Odds are you've figured out there's more things coming in or going out from down here at the bottom. So let's make this our reference node. We'll flag it like that. Okay. Now let's define voltages for the other nodes. So we'll call that one V1 and this one V2. All right, now we've done all of that. That's the setup so that we can write the node voltage equations now. So we'll start here. Let's see. The looks like it's going to be minus 4.5. The current going down is going to be V1 over 1. Plus the current going to the right, that's going to be V1 minus V2 over 678 ohms. And that's equal to 0. There, we just wrote our node voltage equation by inspection. Let's do the same sort of thing now for node 2, where V2 is. Going to the left, that's V2 minus V1 over 8. Plus, going down, that's V2 over 12. Plus, going to the right, that's going to be V2 minus 30 over 4. And that's equal to 0. There we've got our two node voltage equations that we wrote down really quickly. Didn't take us long at all. Now comes the hard part, which is solving them. And you should be able to do this fairly quickly. Let's see if you can rely upon my trick this time. Let's see, common denominator here is going to be 8. So negative 4.5 times 8. I don't want to pause to do that. This is going to plus 8V1 plus V1 minus V2 equals 0. So we've just sort of reduced it down, find a common denominator and make it a little simpler. We can group terms here. Let's see, there's 8, 9v1 minus v2 is equal to, now let's do this.
4.5 times 8 is 36.
36. Now let's do the same thing for here. Looks like, what have we got? So it looks like a common denominator here is going to be 24. All right, so we're ready to write our common denominator here. 8 times 3, so that's 3v2 minus 3v1 plus 2v2 plus 6v2 minus 6 times 30. And that's equal to 0. So we can combine terms here. Looks like we got 3 minus 3. That's 0. So all of the what? What is that? Sorry, v2. Yeah, that didn't make sense. That's a v2. So what have we got? We got 1v1 minus 3v1 plus 6, 7, 8, 9, 10, 11 v2 is 180. So if I did my arithmetic correctly, those are my two equations, and I should be able to solve that pretty quickly. These are the answers you should get if I did this correctly. The book I got this out of says that V1 is 6 volts. It also says that V2 is 18 volts. All right, so how do we find V then? Let's think about this. At this point, the voltage is V. So V1, if the current's going to the right, minus 6I, if we assume this current is I, is equal to V. So if I want to know what V is, I need to solve this. Well, what's I? Look at I. That I would be the current that's going to the right, which is this one right here. So if I take and solve for I out of this using my V1 and V2, and I plug it in here, multiply by 6, negative V2, but you get the idea, and solve for V, then I've got it. And the answer is V equals 15 volts. Final answer, that's it right there. Okay, so V is equal to 15 volts. Now, how did I get that? Start here, write down that voltage. We had a drop, write down that. And once we get there, those two voltages have to equal V, that voltage there. And that's it. Now, my recommendation is that you prove to yourself that these are indeed the answers, and that is indeed the answer. I trust these. This is correct, and that is correct. Okay. Now let's do another one. Okay, here's our circuit. Once again, we've got two sources here, but notice one of them is a dependent source, and it is controlled by this current, which is called I sub phi. So the voltage is going to be 8 times I sub phi, whatever that is. Now, in this case, we'll still be able to write down node voltage equations and do everything exactly the way we did before, but the difference is we have to be able to add one more equation so that we can solve with a dependent source present. So the point here is the dependent source just adds one more constraint, one more equation that has to be part of the system in order for you to solve. Let's follow the rules. First of all, node, essential node, essential node, essential node across the bottom. Let's flag that one. Let's call this one V1. Let's call this one V2. There, that's all the preliminary stuff. Now let's start with here. Going to the left, V1 minus 20 over 2. Going down, V1 over 20. Going to the right, V1 minus V2 over 5. And that's it. That's all the currents. Has to be 0. Equation 2, node 2. Going to the left, V2 minus V1 over 5. Going down, V2 over 10. Going to the right, V2 minus this voltage, and this voltage is 8 I sub phi over 2, and that's 0. So far, it looks very much the same. This is a voltage source, so you just treat it like any other voltage source by V2 minus whatever its value is. But you'll notice here, now we've not just got V1 and V2 in our two equations, we've also got I sub phi. So we need a third equation to relate I sub phi. Otherwise, it's two equations with three unknowns. So to find I sub phi is pretty straightforward. Just look up here. The current that's going to the right out of V1, let's say we go to the right out of V1, well, which current was that? That's this one right here. So that's really I sub phi right there. So there's our equation. I sub phi is equal to V1 minus V2 over 5. So now we've got three equations with three unknowns. You could take this, substitute it in right there, and now you just have two equations with two unknowns. All right, I'm going to leave it up to you to do the algebra here. And whenever you do the algebra, you end up with V1 is equal to 16 volts. V2 is equal to 10 volts. Be sure that you can do that. All right, now we didn't say what we were going to solve for. I guess V1 and V2 could be it. But, you know, if you wanted, let's say, the power for the 5 ohm resistor. So power for the 5 ohm, that's going to be equal to I sub phi squared R. I sub phi, you would have to solve for that. And whenever you do that, let's see. I sub phi is V1 minus V2. So V1 is 16 minus V2 is 10. So that's 6 fifths. 6 fifths is 1.1/5. So that's 1 and 2. So that's 2/10 amps. So that's I sub phi. So 1.2 amps squared times 5 ohms, let's do that math, 7.2 watts. That's the power of the 5 ohm resistor. So that's the power dissipated by the 5 ohm, 7.2 watts. Okay, great. Now hopefully you have a good feel for how to do node voltage equations. I would recommend you learn this method because it's probably one of the most useful ones. Learn it well. You will be using it a significant amount as we go forward. Let's do one other problem, and this will be a special case where we have a voltage source between essential nodes. Whenever you have a voltage source between essential nodes, you treat that like something called a supernode, and I'll show you that. Well, there it is. Here's our circuit. We've got two independent sources here, current source and a voltage source. And then we've got this dependent source at the top. But notice this dependent source, this is a voltage source, that is between two essential nodes. So there's an essential node there in front of it and to its right and to its left. And we've got the other node down here. Let's go ahead and flag that one. All right, now let me show you the usefulness of having a voltage source between essential nodes here. Let's call this one voltage 1, we can call this one voltage 2, we can call this one voltage 3. Voltage 1, you know, by inspection you should be able to write voltage 1 is equal to 50 volts. The reason is because there's no resistance in this entire path from that essential node down here. So the only voltage present is this 50 volt source. So the rise going from here up to that point has to be 50 volts. So V1 is at 50 volts. Okay, that part was easy. Let's look at V2. Now when we write the V2 node equation, we're going to go to the left, we're going to go down, we're going to go to the right. But notice what we get here. V2 minus V1 over 5 plus V2 over 50 plus, now what do we do here? Since we don't have a resistance between these two, but we only have a voltage source, we cannot write a normal equation like V equals IR, or I is equal to V over R. Instead, let's just call it I, and that's equal to 0. Okay, now let's do the same thing over here for 3. For 3, we've got going to the left. If we called that I, then this is the opposite, so that's minus I, plus V3 over 100, that's going down, and now going to the right, it's going to be minus 4. That's equal to 0. Okay, now let's see what we've got here. We've got this equation, we know. We got this equation, looks like V2 and I are the unknowns, and here I and V3 are the unknowns. So we really don't have enough equations. But I want you to notice this. Let's add these two equations together. That's something you can do. I don't know if you knew that, but let's add these two equations together and see what we get. We get V2 minus V1 over 5 plus V2 over 50 plus V3 over 100 minus 4 equals 0. You noticed what happened? The I and the negative I canceled each other. So what we ended up with is one node voltage equation that got rid of that variable, that got rid of that I. And you can do that whenever you have a voltage source between two essential nodes. We are effectively treating this whole thing right here, this whole area, as if it is a supernode. That's called a supernode. And whenever you do that, you still keep V2 and V3 variables, but you write it for everything exiting or entering into the supernode. You don't worry about what's happening inside the supernode. So let's say we did that here, V2. Let's write the current going to the left. Well, that's going to be V2 minus V1 over 5. That's this one. And now going down, V2 over 50. That's this one. And now don't worry about what's happening inside. How about going down? That's V3 over 100. That's this one. And then going to the right, that's this one. So by doing that, we've eliminated that variable about what's happening between these two nodes. So far, V1 we've solved. This is the equation for the supernode. Okay, but really, we still need more equations here to be able to solve this. So let's see if we can come up with those equations. This is one, but we could plug that in here. That's the second one, so that eliminates one of those. And in order to get these other equations, we look at what's happening inside the node here, as well as this I sub phi. You'll see it in a minute. Let's start at V2. Let's go to the right. As we go to the right, we're passing across a voltage rise. And that voltage rise is 10 I sub phi. And then we get here, and that voltage has to equal V3. So here we've got an equation then that relates V2 and V3, but we've introduced another variable here. If we can find a variable for I sub phi, we should be okay then. Let's see if we can find that. I sub phi, you can figure out by inspection. I sub phi is the current that's going away from V2. So if we did V2 minus V1 over 5, that's what I sub phi is. Now remember, this one is known, V1 is known, that's the 50 volts. So let's see what we've got here. This is 50 volts. This is 50 volts. So we've only got V2 as a variable, V3 is a variable, and I sub phi is a variable. So right now we have three equations with three unknowns. There. Now you can do the trick that I showed you previously. You can solve for this, find a common denominator. Should be pretty easy for this one. You can set these up, a V2 column, a V3 column, maybe an I sub phi column is equal to the constants, and set it up like a matrix equation, the way that I've shown you before in class. Set it up like that and use your calculator to solve it. Let me give you the answers though. We already know that V1 is 50 volts, V2 is 60 volts, I sub phi is 2 amps, and V3 is 80 volts. So with those known, then you can get to solutions for everything else. I think you should be able to solve any sort of node voltage problem that gets thrown at you at this stage. Let's do one last one because I like to. Okay, so here's the circuit that we want. This is V0 across the 40 ohm, and that's what we want to find. In the process, we need to find I delta as well. So the problem is given to us this way: find V0 and I delta. Okay, the first thing we need to do is let's find out where all of our central nodes are. Looks like we've got one here, we've got one here, we've got one here, and we've got one across the bottom as well. All of this down here. Looks like all of them have 3 things that they're connected to. So 1, 2, 3 as well here across the bottom. So then it doesn't really matter. We might as well pick the bottom. Now for this one, if I called this V1 and that V2 and that V3, I could certainly do that. But just notice a few things here. First of all, you know what that node voltage is right there. It's 10 volts. There's a source between the reference node and that node, and it has to be 10 volts at that point. Okay, the same sort of thing over here, except you're going through a drop as you go from the reference node to this node. So that's got to be minus 20 I delta. Because why is it negative? Because you're going from the reference node to that node, there is a drop. That's why it's negative. All right, well, that leaves this one right here. What do we call it? Well, you've already got a variable. That's V0. The rise going from the reference node to that point is V0. So, you know what this one is. You know what this one is, kind of, if you knew what I delta was. So we can write a node voltage equation for, well, all of these if we want to, but let's start right here. Let's write a node voltage equation for the V0 node. That's V0 minus 10 volts over 10. That's the current that's going to the left. The voltage you're at minus the voltage of the node you're going to divided by the resistance between the two. That's nothing but V over R. Plus, let's go down, V0 over 40. Plus, let's go to the right. V0 minus negative 20 I delta over 20. That has to equal 0. Now the unknown here is V0 and I delta. Looks like we need an equation for I delta then that involves I delta so that we can figure this out. But before we go to that, let's simplify this a little bit. Looks like what, 40 is going to be the common denominator here. So 4 V delta minus 40 plus V0. I said V delta, that's V0. Plus 2 V0 plus 40 I delta equals 0. So let's combine our like terms here. There's
4, 5, 6, 7.
V0 plus 40 I delta is equal to 40. All right, there's one of our equations that we're going to need. Looks like our unknowns are V0 and I delta. We need another equation, and in order to do that, we need to write another node voltage equation. Now, you notice we can start at one of these side nodes and go across the top as well. So if we write the currents that are leaving one of these nodes, and we should be able to write another node voltage equation. So let's start here with this one right here. I'm going to do that right down here. So we're starting with this node right here, 10 minus, we're going this way, 10 minus the voltage over here, which is already negative, so plus 20 I delta divided by 30, plus, now let's go in that direction, so 10 minus V naught over 10, that's this. And now the current that's going down this direction is negative I delta. You notice I delta is defined here, so it's in the opposite direction, the current we need. When you're writing node voltage equations, you always assume the current is leaving the node, and if you do that, then you can set it equal to 0. Okay, so we need to find our common denominator now, and it looks like the common denominator is going to be 30. So 10 plus 20 I delta plus 30 minus 3 V naught minus 30 I delta equals 0. Combining like terms then, it's like we've got 30, 40, let's put that on the other side of the equal sign. We've got I delta of negative 10, so negative 10 I delta, and looks like we've got negative 3 V naught. There's our other equation. So this equation here and this equation here, so that one and that one are our two equations with our two unknowns at this stage. So we should be able to solve those. I once again will leave it up to you to plug it into your calculator and get an answer. When you do that, you get V naught is equal to 24 volts and I delta is negative 3.2 amps. And again, I feel reasonably confident that those are the correct answers. Of course, you could always build this thing in PSpice and just prove that that is the case. Okay, that's it for node voltage method. We'll do mesh current, and mesh current will go a lot more quickly than this. See you next time. And Bob Trump.
They don't like you, they don't really like you. They don't know you, so why you gotta try so hard to make them like you, to make them really like you? When you tell me that you don't really care what they do. They don't like you, they don't even try to. They'll try to fight you and find a way to tear you down, and it affects you, hate that it affects you. When you tell me that you don't really care what they think. Haters will hate and the players will dream. Then tell me who is to blame when you choose to believe what they think. Don't be dumb, give on the thumb. Don't be dumb, give on the thumb. No, mama, don't be dumb, give on the thumb. You will always be so great. Don't be dumb, give on the thumb. Don't be dumb, give on the thumb. No, mama, don't be dumb, give on the thumb. You will always be so great. Go in your own way. I'm a bruiser, I got so much to show. A stupid jack, I should've looked this time soon. So anti-personal, I'm probably too emotional. But would they listen when they sing you with a voice like that? Critics will write and the singers will sing. And I believed what they said, so you can blame it on me.
Well, I just feel like more of a screamer than a singer anyways. Whatever.
Don't be dumb, give on the thumb. Don't be dumb, give on the thumb. No, mama, don't be dumb, give on the thumb. You will always be so great. Don't be dumb, give on the thumb. Don't be dumb, give on the thumb. No, mama, don't be dumb, give on the thumb. You will always be so great. Go in your own way. I believe Don't be dumb,